Thanks everyone for attending today. So this will be our last session for the year, and then I believe we're having a bit of a break to allow for the study of mean curvature flow to occur in January. So our last talk for the year will be Vishnu, who will be continuing to talk about the Ricci Flow. The topic for today is various maximum principles that can apply to the Ricci Flow. What looks like we'll be looking at the scalar maximum principles. Thanks, Vishnu.
Thanks. So I'm going to be talking about the maximum principles this week. So kind of following on from when I talked about evolution of curvature quantities 2 weeks ago. So I'll start by just proving the weak maximum principle and then stating the strong maximum principle, and then I'll look at some applications. Okay, so then let me just do the statement. Okay, so this is the weak maximum principle. Okay, so then suppose like M is a compact manifold possibly with boundary. And suppose we have a family of metrics GT where T is in some interval depending smoothly on T. And suppose we have some additional objects, a function f from R cross 0, t to R that is Lipschitz in the first variable and continuous in this variable. And also we have a family of vector fields, smooth family of vector fields. Actually, it's continuous as well. On M. Okay. Now suppose that for U in let's just say it's smooth, M cross 0, t, but I guess you only needed to be twice differentiable in here and 1 time differentiable in time. And let's call this one U bar in C infinity 0, t, you have the following properties. So first you have this partial differential inequality. Time derivative of U is less than or equal to the Laplacian, which depends on G of U, plus the directional derivative of U in the direction of X. So plus F of U, t. So this is the Laplace-Beltrami operator. And this here is same as xt in a product with grad U. So that's first property. A second property we need is that U is less than or equal to U bar. Also, this is true on M cross 0, t. And we need this to be true on the parabolic boundary of M cross 0, t, which is defined to be M times 0. So the whole manifold at times 0 has to be true, as well as always on the boundary for all time. Cross. I think this is a open bracket here. So just to draw a diagram of that data set. So if you have your...
You could have close bracket by continuity.
Yeah, of course. So here's M, here is the interval. So here's 0, here's t. And so the parabolic boundary is just this part on the outside. And then finally, third property is that time derivative of u bar has this reverse inequality with f of t for t in 0, t. Okay. Then, if all those properties hold, then u is less than or equal to u bar on m cross 0, t. Okay, so does anyone have any questions about the statement there? One thing, I'm not fully certain about this, but I'm not sure if this property needs to hold on the parabolic boundary if M is compact, because then, I mean, because of this first property here, can't you apply the maximum principle to the boundary? As if you just have this true on M cross 0, then couldn't you apply the maximum principle to the boundary because it's compact, and then you would get that this property is true on this set here. That just occurred to me just earlier today, so I wasn't quite sure. If someone knows the answer to that, I would like to know.
You mean in the case where the manifold has no boundary? Is that what you mean, or the?
Yeah. So the boundary has no boundary.
Yeah,
so...
in that case, there's no sides in this picture then. Yeah.
Oh no,
So...
I mean like in the case of boundary, can't you apply the maximum principle to u restricted to the boundary?
Usually the restriction to the boundary doesn't satisfy any particularly nice equation.
Okay, so this, okay, so you mean this, okay, so then that means that this should be just on the interior.
Yeah.
Yep, okay, that's fine. Yeah, so this is on the interior, this first condition. Then you do need this second one. Okay, so let me now prove this. Okay, so first, I'll prove this by first assuming that, right, so I already just want to see these equations here. First, assume the inequalities in 2 and 3 are strict. So simple case. So then we can take a t star to be in 0, t maximal, so that we have this this inequality here holding. So u for all x, t is less than or equal to u bar of t. For all t in 0, t star. So then, because this inequality in the inequality 2 is a strict inequality now, we know that t star is greater than 0. Okay, so now first suppose that, suppose that t is less than t. Suppose that. Then you can choose a x star in the interior of M, such that u of x star, t star is equal to capital U, u bar of t star, right? And so let me just draw a diagram. So since t star is chosen to be maximal, you know that at x star, so this is capital T over here. This is time, and here is the value of something like that. That's the value of u bar t. And here is t star. And so maybe u something like this, and then it touches there. And so this is u of x star t. Okay, so that means that at this point t star, you have that, you know, the distance between u and u bar is decreasing, so partial. So well, yeah. Firstly, you have that. So you have that partial t of u bar t minus u of x star comma t, evaluated at t star, is less than or equal to 0. And so you have that, yeah, so then you have partial t u x star t star is greater than or equal to partial t u bar x star. I'm sorry, no, there's no x there. It's t star. Okay. But since this, by definition, this is a maximum of u, you know that by the second derivative test, the Laplacian of u at x star t star, that's going to be greater than 0, greater than or equal to 0. Oh, sorry, no, actually, no, that's less than or equal to 0 at the maximum. And also, the gradient of u is equal to 0, since x star is a max. Okay, so then combining all our equations, we have that partial t of u bar at t star is less than or equal to partial t of u x star t star, which is then less than or equal to this. So I'll get rid of the, I don't need to, I can ignore this term here because it's equal to 0, plus f of u of x star t star comma t star. And that's, so this is less than or equal to 0, so that's less than or equal to f of capital U bar t star comma t star, which is strictly less than, by the assumption, time derivative of u bar t star. Okay, so that's a contradiction. So now we just have to do the general case. Okay, so this one, you know, if you've seen the proof, you just kind of modify u a bit. So define u bar epsilon t to be equal to u bar t plus epsilon t plus epsilon squared. So then, I mean, then you immediately have that u bar x comma t is strictly less than u, for some epsilon greater than 0, u epsilon of t. So you have the first strict inequality. So now you just have to, in order to apply this simple case, you just need to get this second strict inequality. Oh, sorry, actually, I wrote the bars the wrong way around. Okay, so now for the other one. So now, since f is Lipschitz in the first coordinate, we know that f of u bar epsilon t comma t minus f of u bar comma t, that's less than or equal to, so there exists C greater than 0 such that less or equal to C times epsilon t plus epsilon squared. But then, that's the same that you can just rewrite that as f of u epsilon t is less than or equal to f of u. Sorry, in my notes I haven't written any of the bars, so keep forgetting to write the bars. Okay, you have u bar of t comma t plus c epsilon t plus epsilon squared. But then you know that we have an inequality for this quantity here that's less than or equal to partial t u bar of t plus c epsilon t plus epsilon squared. And that's the same as, to make this into a u epsilon, partial t of u bar epsilon of t plus c epsilon t plus epsilon squared minus epsilon. Okay, so now, restricting if you restrict to sufficiently small epsilon, you can choose a tau in 0, I guess that's sorry, in open bracket 0 comma t, so that so tau in 0 comma t, which is independent of epsilon, so that tau is less than 1 on c minus epsilon, then whenever t is less than tau, we can do this. C of epsilon t, so the goal is to make this whole part less than 0. C of epsilon t plus epsilon squared minus epsilon is less than or equal to C epsilon tau plus epsilon squared minus epsilon, which is less than C epsilon 1 on C minus epsilon plus epsilon squared minus epsilon, and that is, let me just check, that's equal to 0. Right, so we have this thing is here is equal to 0. So for t in 0 comma tau, we have f of u bar epsilon t comma t is strictly less than partial t u bar epsilon t. And then so you can apply the previous case to the interval 0 to tau. And then then repeat the process. I guess you can just repeat the process at t equals tau, right? And then by compactness of the interval 0 to t, you can extend this to all of the interval 0 to t. U less than or equal to u bar on m cross 0 comma t. Yeah. Does anyone have any questions about that?
One quick question. Is F assumed to be positive? Maybe I missed it.
No. I don't
Okay,
think
so how does the inequality after the Lipschitz assumption happen then?
Oh, yeah, let me see.
Yeah.
Let me. Well,
So the
Yeah, so I mean-
f of u epsilon minus f of u bar is less than the absolute value.
Oh yeah.
Yes,
Okay,
yes.
sure.
So yeah, it's
Yeah.
plus. Yeah, just plus or minus this one
Clearly.
is less than this one, so you can just
Yeah.
take the plus one. Yeah, yeah.
Yeah, obviously. All right, cool. Thanks.
Maybe
Okay.
the moral of the story, right? Just to summarize, because it's a long proof and it might look convoluted, but I guess the statement is very easy to remember, right? I mean, if you've got a solution to the parabolic equation, then if you have another solution to the ODE, then you can compare to that one, right? So
Yep.
essentially,
Yep.
you can ignore the PDE part if you're lucky, right? And that's super helpful.
Yeah. And maybe I didn't mention, but you need compactness for choosing this X. I forgot to mention at the time. So that's why I needed to choose a compact thing. But actually, if you wanted to get rid of your compactness assumption, then you can just put in a property that ensures that this that a maximum such like this occurs. Okay. So yeah. So now I'll state the strong maximum principle. So strong maximum principle is basically says that the equality, either this just is completely inequality or it's a strict inequality. That's essentially what the strong maximum principle says. But it doesn't apply to not just compact manifolds. So the strong maximum principle. So in this case, M is connected. And again, with boundary and with boundary. And you have the metric GT, comma, XT, comma, F as before, as in the weak maximum principle. And suppose that for U and U bar, as before, assume they're smooth, we have partial T U less than or equal to TU plus XT U plus F of U comma T, and U is less than or equal to U bar, and where both of these are on M cross 0 comma T. So you kind of like you are assuming the conclusion to the weak maximum principle. And again, you have this thing here, partial T U bar greater than or equal to F of U bar comma T for T. Then if at ux0 comma T equals U bar of T for any x0 in the interior of M, then U is equal to U on M across 0, t. So another way of phrasing this last sentence is that if you can only unless u is constant, unless u is identically equal to u bar, you can only be equal to u bar on the boundary of M. So that's why you have the int M. Okay. So yeah, so this either you have a strict inequality here in the weak maximum principle, or you have a full equality. Yeah. Does anyone have any questions about the statement of the strong maximum principle? Okay, so now I'll do some applications. So applications. Okay, so remember that last week I did one of these evolution equations for the scalar curvature. Time derivative of r is equal to fraction of r plus 2 times the norm of the Ricci curvature. So I want to simplify this a little bit so that I can get a useful inequality that I can apply. So first, remember that you can write the Ricci curvature in terms of its trace-free part plus another part. So this is again the scalar curvature. And if you just take the trace of both sides, you'll see that by definition the trace of the Ricci curvature is the scalar curvature. So this makes sense. You just define this thing, the trace-free Ricci part, to be Ricci tensor minus this quantity here. And well, I mean, what does trace-free actually mean for a 2-0 tensor? It just means orthogonal to the metric. So you can see that immediately this thing here is an orthogonal decomposition because G ring 0 G in the inner product is by definition Gij Ij, which is equal to 0. So then you know that the norm squared is equal to norm of this plus 1 on n r squared, which is then greater than or equal to 1 on n r squared. Okay, so this thing here, that's greater than or equal to the Laplacian of r plus 2 on n r squared. Okay, so this is what I'll use. Okay, so first application, so let's say m comma t for t in the interval 0 comma t is a Ricci flow, and let's say m is compact without boundary. Yep, then if the scalar curvature at time 0 is greater than or equal to c, then it's greater than or equal to c for all time. So for this one, you well, you already know that you already have this partial differential inequality here. So we need to find the other two inequalities. So choose, well, I guess f is defined to be 2 on n u squared and u bar to be just the constant function c. Right, and then you know that partial t u bar is equal to 0, which is less than or equal to 2 on n u squared. And then apply the weak maximum principle, right, which will imply that r is greater than or equal to u bar for all time. So you get this thing here. Okay, so scalar curvature is always going to increase, but that's a very that's a bit weak. That's a bit of a, you know, you could have done a lot more, because I've just chosen something that is, I've just made this thing here be an inequality, but if I try to make it an equality, I'll get something stronger. So let's do that. So same situation. So if r is greater than or equal to c as before, then r of a t is going to be greater than or equal to cn on n minus 2ct. So for this one, again, f is given as 2 on n u squared, but then now u bar is chosen so that it solves this equation. So u bar partial t u bar is equal to 2 on n u squared, which implies that u bar of t is equal to c n by n minus 2ct. Okay, and then again apply the weak maximum principle. But the one consequence of this is that if t is maximal, then you would expect that this quantity here, you know, the scalar curvature becomes unbounded as t approaches capital T. So you would expect that n minus 2ct is equal to capital T. Well, actually, maybe I'll phrase it this way. Oops, sorry. Yeah, so clearly the scalar curvature becomes unbounded when this equals 0. So if you solve for n minus 2ct equals 0, then you get that t is equal to n on 2c. So you expect that the maximal time that this can exist is going to be less than or equal to, I guess, yeah, less than or equal to n on 2c. Yeah. So in this case, we have, we know that in finite time, if the scalar curvature is not everywhere 0, if it's greater than some value, then for all time, the maximum time is bounded above like this. Okay, so now maybe I'll go look at an application of the strong maximum principle. Oh, actually, maybe I won't have one more thing written down here. So if t equals infinity, then you know that for that to be true, c has to be equal to 0 here. Otherwise, the maximum time is going to be restricted to be finite. Then you need r, t greater than or equal to 0.
So c can be negative here, right?
Yeah.
That would also allow infinite time.
Yeah, that's true, correct. Yeah. So if c is positive, I guess I should put c greater than 0. Yeah.
So So I think this is a bit misleading, right? That just the last statement, the previous statement are fine, but you cannot deduce positive scalar curvature from the fact that
That's
flow exists
true.
for all
Maybe
time, right?
yeah, that's true. I think
Like
I should,
a hyperbolic manifold is a counterexample.
Yep.
It expands forever, but it has negative curvature.
yep.
Yeah. Which your
yeah.
computation does there quite nicely. So that gives you the value of scalar curvature on a hyperbolic manifold if you take a C negative there.
Yes.
Yeah.
Yeah. Yeah. So that's good. So yeah, I'll do an example of the strong maximum principle that I could use it. So suppose n is disconnected, and scalar curvature is greater than or equal to 0. If the scalar curvature at x0, t is equal to 0 for some x0 in M, then it's equal to 0, identical. But and then another consequence of this is that just looking at the evolution equation for scalar curvature, so this is then equal to 0, and this is equal to 0. So this is also equal to 0. So you also get that the Ricci curvature is identical equal to 0 as well. So then, yeah, that's an example of strong maximum principle. And then okay, then let me see what else should I go over. Okay, yeah, I wanted to do this example in dimension 2. Does anyone have any questions for this question number 3? Okay, so in dimension 2, the only non-zero components of the Riemann curvature tensor are also in normal coordinates. In normal, you have that the only non-zero components are given by the Gauss curvature, which are R1, 2, 2, 1, R2, 1, 1, 2, which is minus R1, 2, 1, 2, equals minus R2, 1, 2, 1. And then the Ricci curvature, Ij is given by R1 Ij1 plus R2 Ij2. And so you get Ric 1, 1 equals K. Ric 2, 2 equals K, and the other ones are equal to 0. So that means that the scalar curvature R is equal to 2K, just by summing these two. Yeah. Also, if you look at the trace-free part of the, so you know that, well, just by looking at this expression here, you know that Ricci tensor is then equal to R divided by 2 times the metric, which means that the trace-free part is equal to 0. And so the norm is equal to half R squared. So then our evolution equation for the scalar curvature becomes partition of R plus R squared. So then I'll try to apply the maximum principle to this. Oh, well, actually, so this is kind of what we used in the previous ones, except rather than having an equality, it was an inequality. So this time we have an equality, so you can use the reverse inequality from. So previously we had this was a inequality here, but now we can, since for dimension 2 you have an equality, you can also make this direction. So that means that if you have 0 less than or equal to 0, then or t comma 0 is less than or equal to 0 for all t. So having scalar curvature negative is preserved in this case.
Dot comma t, I think.
Oh, yep, sorry. Yep. Yes, okay. So that's the thing. I think I'll stop there. That's what I have to talk about today. Does anyone have any questions about this?
Thanks for your talk, Vishnu.
No.
Let's thank the speaker.
Thank you.
Yes, as Vishnu suggested, does anyone have any questions for him at this point?
Are we doing the tensor maximum principle as well later on?
Well, yes, that'll become quite important when we're looking at bandwidth stuff. Yes, I expect looking at the other tensor maximum principle might be one of the things we do pretty shortly. All right, well, as I suggested, we're now having a rather elongated break. So yes, Christmas, and then I believe we won't be having any talks throughout January. This is to allow the students taking the mean curvature flow course to not get distracted by Ricci Flow while they're doing mean curvature flow at the same time. So if you're participating in that, I wish you luck. And I hope everyone has a good break, and I hope you all enjoy your Christmas. So thanks very much for participating, and I guess we'll see you all next year, hopefully.